And so just to remind everybody, the session is being recorded and will be made publicly available on YouTube and through ESTA for others to have for future reference. All right. So we'll start off with introducing our today's panelists. Scott, you want to introduce yourself?
Sure. My name is Scott Blair. I'm newly with Megapixel VR. Been a member of the Control Protocols Working Group for longer than I care to think about at this point, and chair of the RDM Net Task Group, as well as the member of the E1.31 Streaming ACN Task Group.
All right. And I'm Eric Johnson. I've been a volunteer for the Control Protocols Working Group, working on RDM and the network protocols for several years now. In my day job, I work for Cisco Systems, but today I'm just here in my capacity as a volunteer for the CPWG. We do want to emphasize that today's discussion is based on Scott and my personal interpretation of the standard. What we're doing does not constitute an official ESTA action, and is certainly not a override anything in the standard. Scott and I are frequently wrong and reserve the right to be corrected or other things that may come up.
We reserve the right to be wrong.
And frequently are. So, with that, a brief overview of our agenda. We're going to talk a little bit about some background on the protocols itself. Most of you who are interested enough to be here will be aware of that already. Then about universe synchronization, what does it solve, what does it do, how does it work? And then we'll try and reserve some time for QA at the end. We'll probably go a little past an hour, but we'll just kind of see where it goes and what the level of interest is. So, with that.
Sure. So, people ask, what is E1.31 Streaming ACN? It's, as most of the people I think that are online here know, it's a protocol for transporting DMX512 style data over an IP network. Similar to ArtNet, but a little bit more network friendly and has a bit tighter defined rules. It's a formalized standard that's published under ANSI in 2009 was the first release. We've revised it a couple times since then. The current revision that's available right now, it was published in 2016, which added universe synchronization and universe advertisement. We're really not going to talk about universe advertisement tonight, but in general, it just lets other devices on the network know what sources are out there and what universes they're sending. There's a 2018 revision that we have just finished up on and should be getting published in the next couple months here, which fixed a few small errata, as well as adding IPv6 support. So there's an option, there will be a forthcoming option for doing streaming ACN with IPv6, should you so need. As the next bullet point shows, it's colloquially called streaming ACN. There's full ACN and streaming ACN. We'll talk about that just briefly in a second. But we are talking here about streaming ACN, which is, as many people know, like I said, similar to ArtNet. One of the benefits of streaming ACN is that it requires very little configuration, especially on small systems, but it allows you to scale very well to use your proper network infrastructure very efficiently for large systems. We do this by using multicast. Streaming ACN allows for unicast, but by using multicast, it allows us to be much more efficient on using network infrastructure for sending one universe of data from one device to many devices that need to consume it. As a protocol, it's very widely implemented at this point across a lot of vendors. So most products out there that support ArtNet at this point, many of them or most of them are starting to see streaming ACN supporting them as well. And as I said, we talk a little bit about the relationship between ACN and streaming ACN. ACN, full ACN as it's often called, is published under ANSI E1.17. It's a framework for carrying show data across a network. And by show data, I mean any kind of data. It was really meant to encapsulate the entire universe of the sun, moon, and stars. So it wasn't limited to just lighting. It was meant to be used for audio. In fact, there's one company that does use it internally for audio, as well as show control data, lighting data, scenery data, anything you can imagine. So it can carry many different kinds of data. E1.31 is specifically really just how to carry a universe of ACN, a universe of DMX512 across the network using the ACN packet format. So it really doesn't share much with full ACN other than it uses the same packet format so that if you were in a full ACN environment, at least it would be able to understand what the data is. It would understand how to parse it. And I'll let Eric here pick up the terminology.
Sure, just some terminology that we will use. A universe is defined in the standard as a set of up to 512 data slots identified by a universe number. I think we all know what a universe means. We have a concept of it. E1.31 just allows you to tunnel a bunch, one or more universes over a network. The term that we use for something that sends a bunch of these packets is a source. So we have sources and receivers. Elsewhere in standards, we have sources and sinks, we have controllers and responders, we have senders, we have consoles. The terminology we try to use here is that of source and receiver. And the term synchronized in this context does actually have a technical meaning. It refers to a receiver that is actively receiving sync packets. We use it a little more casually also, but that's what it does mean in the scope of the standard.
So one of the questions, why do we need synchronization? Back in the olden days here, which was not that many years ago, before the onslaught of LEDs, it really didn't matter because everything was incandescent. So the response time of a filament in a source 4 or in a power lamp is slow enough that if you had synchronization differences between multiple universes, you wouldn't really see the issue so much. Also, a few years ago, we didn't have the explosion of the quantity of universes on the show as well. So one of the issues we see here is you have more universes of data being sent by a console, and they're all coming out at slightly different times because the console can't send all the universes exactly at once. So you end up with some small delta of time, and as you start getting more and more universes, it starts adding up. And then when you go from incandescent to LED fixtures, which respond very quickly, you can then start to see the artifacts of that small time difference. They really start stacking up. And we've had these problems for years in moving lights, though, in strobe lights, where you would have problems if you're trying to do a synchronous strobe through a console that has uses gateways, where every universe is not coming from the main console itself, but it's coming out of different gateways. You might see synchronization issues there with the strobes, where strobes coming from one universe or from one gateway are slightly different, slightly different points than the other. The way a lot of moving lights dealt with this was by synchronizing to the break. So within a universe, it was able to be synchronized very tightly, and then you relied on things like the gateway to synchronize the universes over DMX512 being put out very close together to minimize that. But once you have multiple gateways, unless you had some type of network synchronization, you would fall back to the same problem. And as we said here, modern LED fixtures and video displays, even as we're seeing a lot of, they respond very quickly. Your eye can really pick up the differences very fast, and especially if you're doing something that's televised. If you're doing something that's televised or on camera, the sampling time of the camera will really start to magnify it even more of what somebody sees through a monitor.
And so one of the quirks of all of this was that when you synchronize to the AC line, you move your show from a 50 hertz country to a 60 hertz country, and the timing of your show looks different. So kind of some of the unintended side effects of technical decisions. So something that comes up a lot. What do synchronization problems look like? So we're going to present some concepts here to help you sort of visualize and then to have a word to talk about what you're seeing if you see this happening on your shows. One of the concepts is that of tearing. Now, in progressive video or progressive scan video, like you get with NTSC or PAL or under the newer HD standards, tearing does have a very specific technical meaning. We're extending it a little bit here because when we have large pixel mapped arrays, they tend to be broken up into even more smaller universes than you would see. But what I'm showing here with the picture of the stoplight is a simulated example of tearing where you have this pixel map grouped across a number of universes. And effectively, during a fast scan, what you see, during a fast pan right or left, you see that sometimes, at one point, you're seeing some old data, because the old data hasn't gotten there yet, and some new data. And so you effectively see a tear. You see a line through the middle of your image. Other things that can happen with, take these examples over here. If you're doing a color bump, say you have an upstage wall of RGB par cans, or there's an upstage pixel wall, and you want to do a quick transition from yellow to blue. Ideally, you want all of them to transition at the same time. But if you have synchronization problems, and one tile's universe doesn't get there, or one block of data doesn't get there, you get an interstitial state that looks something like this. So most of your array has gone blue, but you still have this one chunk that is yellow in the middle. And then when that data eventually arrives, you now get the full blue. We'll talk about timing on this a little later. And you can get tearing effects on linear arrays too, and I show that example here at the bottom. I think we've all done the row after row of strip lights. And if everything doesn't get there at one time, you see one strip light or group of strip light or group of cells where you have the old data. If you're doing a fast color bump, a fast intensity bump, it can be very obvious. If you're doing a slow fade, maybe you'll see it. Maybe you won't. The other effects you can get is stuttering. Really, these are all the result of the same thing, but stuttering is where and this is a graph of a time versus intensity transition, where what you want is just a nice, smooth, even fade. I think we've all seen this, right? We've all been staring at fades and really seen what a good fade looks like. But when you get steppiness, when you get jumpiness, you can start to see things like this, where you miss a packet and then it jumps to catch up. So stuttering and tearing are kind of the terms that you can use to talk about this and to know what you're seeing. Sometimes if you don't have the vocabulary to talk about it, it can be very difficult to discuss. I want to talk a little bit about the human psychovisual system here. The human visual system is amazingly complicated, and the result of many years of adapting and evolving to our environments. One of the key studies in human perception of time images was done by Max Wertheimer in 1912. It's kind of the beginning of the Gestalt movement, kind of a lot of sort of human characterization work going on at that time. Obviously, I'm not a native German speaker. I can't even read a word. I have the title of his actual study here, and this is public domain, off copyright. And these images were adapted from his original study. But what Wertheimer et al. Realized was that if you take two images that look like this, you take an image presented on the right side of the visual field and then one slightly to the left of it, and you flash those using the technology that was available in 1912. If you flashed the two, and just a brief flash, and you presented them 30 milliseconds apart, it looked like a simultaneous flash. It looked like you were getting two things at the same time. So it would look like this. But if you presented them more than 200 milliseconds or more, and this is, plus or minus, but if you presented them more than 200 milliseconds apart, you would get effectively a flash, and your eyes would see that it was two separate things being presented. But in between that 30 milliseconds and that 200 milliseconds, something really strange happens. Around 60 milliseconds, if I present them and then 60 milliseconds later flash the other one, it looks like a single block that is moving. Now, I think today we all know this. This is how video works. This is how your 60-frame progressive video, your 30-frame video, this is how we can, or your 24, 48, let's not get into the arguments of motion video. This is how our eyes make a movie look like a movement and not just a series of flashing images. But in 1912, this was groundbreaking. And it really was some of the early attempts to characterize how humans see. So why do we care about this? Well, if we have synchronization problems, and instead of presenting things simultaneously, it can look like your lights, like the things you are presenting, are moving, when really what you want them to see is a static image or a static picture. Wertheimer's work led to tons of other people doing similar studies. The whole Gestalt movement went on for more than a decade, and obviously there was a small interruption of World War I in here. But this work is still the foundation of much human psychovisual research. Scott, you want to?
Sure. So, some of the general guidance out of all of this is, when we talk about synchronization, you really want to keep anything that's a direct view light source. So we see it a lot in stage design these days, where we've got LED fixtures or LED arrays that are meant to be viewed directly. They're pointed right at the audience. So you really want to keep those to within about 15 milliseconds of each other in order to minimize the tearing and the effects that we're talking about. If you keep them within that kind of time frame. If you have an indirect view source, such as something lighting the stage itself, not pointing out to the audience for a visual effect, then you can have a lot looser timing. You can get away with it without being as noticeable.
So, Michael, have you any questions come in at this point? All right. So, all right, the plain language walkthrough. The concept of universe synchronization is relatively simple. Hey, Milton, here's a universe of data. Here's another universe of data. All right, I've got another one, and you're a 4-port node, right? Here's 2 more. All right, all that data I just gave you, present it now. Think like a stage manager. Stand by LX41. LX41, go. In the end, that's what we're doing here.
And the key thing to note here, what's different about this is with sync. Without sync, what you would normally see is as each universe of data comes in, as a fixture gets a universe of data, it's going to respond to it immediately as soon as it gets it, even though the next universe is still being sent to the other devices. So that's really the concept of having a synchronization packet, that everybody waits until they get the sync packet before they output their data, versus everybody freewheeling and outputting the data as they get it, is really the fundamental change here.
So in E1.31 Streaming ACN, each universe of data can be assigned a synchronization address. And a sync-aware receiver waits, it gets data when it gets it, but it waits to present that data, to act upon it, until it gets a synchronization packet. One of the key things here is that this is all internal to the protocol. The user experience, what the person using the node, using the gateway, using the media server sees, is the same thing that they had before setting up an E1.31 system that was built to the 2009 version of the standard. All configuration is done at the source, and the receiver still only needs to be configured with the universe number. Scott did want me to point out that, universe and starting address. Many systems do allow you to sort of, pick a starting address in the universe and break your universes up. From my point of view, we are really trying to get people away from thinking of the slot as their quanta to thinking of the universe as their quanta. We all come from the days where the 2-universe console cost a lot more money than the 1-universe console, and getting that 3rd universe cost you tens of thousands of dollars. So we try to cram stuff onto universe. In the brave new world of networking, universes are cheap. So the quanta of data really, in this, it's best to think of it as a universe. Now, obviously, most of the systems need to be commercially viable. They certainly do offer features that let you break up and reassemble and mix and match universes.
And I'd also say it depends on how many channels of data, particular slots of data, faux pas there, how many slots of data a fixture uses, and how many of those you have. If I've got 2,000 LED fixtures that only take 5 slots of data, I'm probably going to want to pack those into a number of universes rather than necessarily giving each one a particular universe. But as you get into some arrays, they take you can't get that many pixels of RGB data on a universe. So you're still going to end up using a lot of universes. And if you have a large array of fixture, or a fixture that is a large array of LEDs, you can very easily chew up a universe per fixture.
So the standard allows that you can have multiple control, you can have multiple sources, you can have multiple receivers, and the same thing applies for sync. And we'll talk about that a little bit more later. But one thing is that the source providing the sync for a universe data must come from the same sender as the data packets. So the sync and the data, this is all within the scope of what is sent by a single media server, or a single input gateway, or a single console. This does not offer a genlock-like behavior where you have a global sync packet that is synchronizing everything on your network. A suitably clever implementer might be able to use this kind of that, where there would be one master sync that would then, the others who would then generate their own slave sync. But at a protocol level, this is not genlock. This is not genlocking your studio. This is just genlocking everything coming from a single console.
I think one other thing to note here while we're on this, we talked a lot about configuration of the receiver side, but even on the source side, it's up to because I know we have some product developers out there that are online tonight. Even on the console side, on the source side, you don't necessarily even need to expose a bunch of configuration to the user. The configuration can be as simple as allowing the user to pick, which universe other things sync to. Of course, this could all be completely hidden from the user and done under the hood inside the console as well. So it's from a user standpoint, it's actually, we've tried to make it very easy to build a synchronized system using E1.31 that doesn't actually require the user to really know anything or configure anything other than making sure that they have devices that all support synchronization features.
So Scott, you want to talk about the two packet formats?
Sure. So on the right here, you'll see an E1.31 data packet. If anybody has cracked open the standard before, this will look, or implemented it, this will look very familiar to you. In the 2016 revision of Streaming ACN, we also added another packet type called the Synchronization packet. Basically, to differentiate them, to get down into the bits and bytes here, there's a different vector, different layer vector, and framing layer vector to differentiate so the device knows whether it's a data packet or sync packet. You can think about this in terms of, in DMX512 and RDM, where we have a start code essentially, so that we know if this is a null start code DMX packet or if this is an RDM packet using a different start code. So it's basically the same concept. We've had the very familiar data packet over here that delivers the universe of Streaming ACN, and then on the left we have a much smaller sync packet that then is the synchronized command that tells everybody to respond. And one of the key things is keeping the sync packet small, because you want everybody to receive that and process it as close to the same time as possible. You want to keep the packet as small, so there's as little overhead as possible for a receiver to process it.
So we're going to dig in a little deeper to the actual packet format here. Now, this packet is copied right out of the standard. The standard is freely available, so I'm not going to go into every field of this packet. If you've implemented E1.31, if you're familiar with the standard, I'm only going to highlight the differences, because this looks a lot, this from 2016, looks an awful lot like the 2009 version. So the data packet, almost everything over here is the same, except for these two fields that we call out here. Previously, bytes 109 and 110 were reserved, and it basically said that they had to be sent as 0 and that receivers should ignore. So we have repurposed those to determine the synchronization address. At one point it was called the synchronization group. It's basically what address should this sync to. And then we added another options bit called force synchronization. And we'll talk about this a little bit more later on. And I just want to emphasize, as you see at the end of the packet, here's the variable size array of DMX512 data. This is a chunk of DMX data that is put together at the end of the packet, and this is fundamentally what this whole protocol is transporting. Scott, you want to talk about the new sync packet?
Sure. So as we said, this was added to the 2016 revision. It's sent to the multicast address for the universe with the same number, and then a much smaller data packet as we talked about. So the key thing here is when we send the sync packet out, it goes out on a specific multicast address, which equates to a specific universe. So let's say we want to have all of our universes. I've got universes 1 through 10, and I want everything to sync to universe 2 for some reason. So universe 2 is the universe this sync packet will go out on. It will not go out on the other universes. All the devices that are on universes 1 through 10 on all the other universes, they will subscribe to the universe that they're getting their data from, but they will also subscribe and listen to the sync address, which will be universe 2 in this case, and that's where they'll get the sync packets at.
So, in the newly defined portion of the data packet, there's a force synchronization bit. This defines what should happen when the receiver stops seeing sync packets, but is still receiving data packets.
And that's the key thing here as we talk about all of this is this really only defines, this bit only defines what happens when after things have been synced and operating and then sync suddenly stops.
So basically, if this bit, and the polarity of this bit for software developers is actually the exact opposite of what you think it would be given its name. A 0 means that you basically, you wait for sync. If you're not getting sync, you don't present the data. A 1 means that if synchronization times out, which is defined as 2.5 seconds without a sync packet, that you just go back to freewheeling, that you play out the data whenever you choose to. And as Scott mentioned, this only defines what happens when sync is lost. One of the quirks of the standard is it doesn't explicitly say what you should do when you start up. We have a little bit more about that later, so I'm going to punt on that for now.
And also the timeout, as you can see here, is after 2.5 seconds is when you consider sync lost. So if I've gone for 2.5 seconds and I've not seen a sync packet, then I can consider that to have lost sync, and then I would then look at the forced synchronization options bit to decide what to do.
The next part of the packet is we need to talk about sequence numbers. Within the packet, there is a sequence number. Data packets and sync packets both have sequence numbers. Why do we have a sequence number? Well, a couple of things. If you miss a packet or two, it's a way to tell that your network is losing packets. Most receivers don't do anything with this, but if you've got a packet analyzer, it's really nice to tell you, why is my thing getting jumpy? The other thing that it can be handy for is actually you can raise an error flag or log an error in a receiver if you're missing too many. But also, sometimes you have people who are using, for example, E1.31 playback systems that are just playing back a looping construct. The standard is written such that if you see a large jump in sequence numbers, you assume that it's just a completely new source of data, or that it's gone back to the beginning of a loop. And so rather than making you wait for a timeout or something, that you just know, okay, I'm playing back a loop, jump. And that behavior was already defined in 2009 and continues into 2016, and I believe continuing into 2018. The important thing I want to call out here is that there is no implied relationship between the synchronization packet, synchronous number, and the sequence number of the data packet. This is not a case where my sync packet, sequence number 1, 2, 3, has to have the same sequence number as my sync packet. Because of data suppression, these are not all walking along lockstep. If you go into data suppression, your syncs may still be going, your things may come and go, different things may get different sets of universes. So within each stream, within each universe of data, there is a sequence number. And within each universe's sync, there is a sequence number. and they can jump all over the map. So universe 1 may have maybe going 1, 2, 3. Universe 7 may be going 48, 49, and 50. And your sync packet may be 591. This is really not intended to say 549 synchronizes data packet 549. That is a key concept here, and if you don't follow that, you will break badly. Before we go on, I'd like to just do a quick poll of the people attending, both in the room. So if you're remotely, if you look under the list of participants on the right-hand side, you see a checkbox for yes and an X for no. How are we doing? Are people finding this interesting? Is it helpful? Is it covering the kind of material that you'd hope that we would cover? Okay.
Have you fallen asleep?
Yes, if you've fallen asleep, please press the, okay. Good. And again, you are free to submit questions in the chat panel to all panelists at any time. And we'll just plan on keeping to go. Yeah, Milton.
The question I have is there ever is there a requirement to buffer up multiple packets or a sync for whatever packets you happen to?
This is isochronous data. You play out the most recent data. In E1.31 and streaming protocols in general, newer is better. You'd rather lose data and get the most current than play out everything that you've gotten before. Because you don't want errors to accumulate over time. If I drop a pack, if I get a little delay now, I don't want a 1 millisecond error once a second to accumulate over the course of the show, because by the end you can build up quite a bit of error. So this is isochronous data. Yeah, we have a question online.
Yeah, we have a question from Matthias about what happens to receivers that don't know what to do with the sync package. Any concerns with compatibility?
Sure, and actually, if you don't mind, we'll put you off. We actually do talk about that later, because that is an importance. The standard was written to maximize compatibility as much as possible, and we are not aware of any concerns in the field. We'll pump the rest of that answer, because we actually have the text from the standard and some of the guidance on that. And if we haven't answered at the end, please feel free to raise that again. All right. All right. Well, I guess we're off to a good start. We're about a half hour in. I suspect we will go a few minutes over. Synchronization on the wire. What we're presenting here is a time view of the most basic synchronization operation. As you know, in E1.31, each universe is sent to its own multicast address. And so each lane here represents a universe's multicast address.
And again, this is all coming from a single controller here.
Correct. Everything is being sent from a single source IP address, single source SID, whichever term, way you care to track it. We have 3 universes that are all being synced to everything. Just a little bit of note on the legend. The bicolor blocks are data packets, and the sync packets are synchronization packets. They're smaller. That's why I present them this way. You play out universe 1 on its multicast address. You play out universe 27. You play out universe 56. But you notice that the sync address field in all of these packets is sent to 27. So after these all been sent, then the sync packet is sent on universe 27. When this packet arrives at the black line here, that means present this data. And we'll talk about timing a little later. But this is the most fundamental use of synchronization. We send out a bunch of universe data, and then here's the stage manager's LX41 go. But you notice that this sync packet goes on the same multicast address as universe 27, but it is a different packet format. This opens up some interesting corner cases that we'll address later. Scott, you want to talk about multiple sync groups?
Sure. So it's also possible, again, from a same source or in different sources, you can have multiple sync groups. So in this case, we've got more universes here. As you can see, we've got 127. Sorry.
This is the same group of universes as the last slide.
Yep.
We've added another sync group.
Right. So you can have multiple sync groups. So if I want to have, for whatever reason, I want to keep certain things synchronized with each other. So maybe I want to synchronize my media servers differently from my LED fixtures for whatever reason there is. The standard does allow you to basically have multiple sync groups. So you can see that in the case here, I've got multiple universes that are synced to 27, 3 universes that are synced to 27, and then you can see the sync packet for 27, goes out later. And then lower down, you can see that I've got 2 universes that are synced to 311. 311 and 312 are both synced to 311. And then you can see I've got another universe down here that doesn't sync at all. So it just plays immediately. And in the case here of the different sync groups, maybe I want to use we talked about the force synchronization bit here earlier. Maybe in the case of the media servers, I want to keep them synchronized. So I would turn the force sync bit on so that so that I don't have any stuttering if sync drops momentarily, but I still want the lights to stay on. So in the other 2 universes, I leave the force synchronization bit off. That might be one use case, but the standard is flexible enough that it does allow you to have multiple sync groups coming from a different from the same source, but completely different sync groups at the same time.
And obviously, you can't send these overlap just because we run out of horizontal space on the slide. You can see that these are sent sequentially. 1, then 27, then 56, then 311. But the key thing to notice is that the universes here are actually played out in the opposite order from which the data is sent, because universe 600 is not synced and plays out when it is received. Then 311 and 312, which are synced to 311, play out, and then 127, 56 play out. So it is the order of arrival of your sync packets that matters, not the order of arrival of the data packets. And that's been the exact opposite of what we typically see. When you get DMX data, you play it out. So this is different from what we've seen before. I want to talk about the idea of a sync-only universe, and I actually use this slide to bring up a corner case. We're trying to use the same set of universes in all of these slides for consistency, but you notice that in this case, 127 and 56 are all synced to 311. But there is no data packet being sent on 311. 311 is only carrying sync data. Why would you want to do, for these, so for the top 3 universes here, they all sync to 311, and 311 doesn't carry data packets. Why would you want to do this? When you get into really large networks, and I'm not talking a 40 universe network, I'm not talking most regional medium-sized shows. This is theme park scale stuff. This allows you, for your network equipment, to be able to administratively groom the handling of sync packets differently from your data packets. For those of you who have a networking background, sometimes you need to apply QoS, quality of service, and class of service prioritization to your sync packets. Because in a large network where you have multiple hops, you can send your data packets and let them take however many milliseconds they need to get there. But you need to minimize the delay skew. You don't want one packet going off to one corner of the rig to take a lot longer to get. You don't want the sync packet taking a lot longer to get to one corner of the rig. So this allows you to administratively prioritize the sync packet based on it being in this sync-only universe. Most of you will never have to care about this. Most of you will never have to think about this. But when you start getting into the theme park scale networks, the huge multi-venue facilities, this is where this starts to matter. The protocol is designed, as we said earlier, to just work for small and medium, but to give you the tools that you need to manage it in larger networks.
And another case where you might also want to use this is let's say if you're want to add sync into some products that are very limited in their capabilities of handling more than one universe worth of data. This allows you to put the sync on another universe where it's not going to have to be dealing with the other stream and flood of universe traffic coming in, of data packets coming in.
So I actually use this one to kind of hide a little corner case on you. You notice here that universe 312 syncs to 27, but universe 27 doesn't sync to 27. I don't know why you do this, but it can happen. So we pointed it out. Universe 27 syncs to 311, and Universe 312 syncs to 27. 27 doesn't sync to 27. Just something to keep them, when you're testing your implementation, be aware that this can happen. I don't know why the heck you do this. Maybe you had a big video wall synced to something and you didn't want to reconfigure a bunch of other stuff, so you just kind of left it where it was, but it needed to go off somewhere else.
And the key thing here is we've kept the rules very simple. So for a receiver, even for a controller, the rules for doing sync are very simple. But it just does allow that you could have, like, something that wouldn't necessarily seem logical maybe for you to configure. It does allow that to happen just because we've put in some very basic, simple rules.
All right, Scott, you want to talk about missing synchronization?
Sure. So, one of the obvious things that could happen here is I'm receiving, I'm synchronizing 3 universes here, and then I lose the sync packet for whatever reason. Maybe the console doesn't send it. Maybe the network ate it. But it could happen. So if I drop a packet, if I drop a data packet, there's another one coming right away. If you drop a sync packet, there should be another one coming right away too, because you're sending data packets. You should have a 1-to-1 correlation of sync packets to data packets. But in this case, I've sent out my 3 universes of data, but there was no sync packet. And then I get another packet of data for those 3 universes, and then I get the sync packet. So what do I do here? In this case, the first universe of the first data packet that comes in, you throw it away. If I get a packet of data, I don't get a sync, but I get another packet of data. I throw away that first packet of data, and then I only act on the last packet of data before my sync occurs. That way, again, you don't get tearing. Everything is in the same state.
And this really goes to Milton's question earlier on. You do not queue up the missing packets. You throw them away. So isochronous data, better new than everything. So we talked about if you miss one sync packet, 2 sync packets. What happens if your sync is missing for a long time? Well, at that point, the behavior depends on the forced synchronization bit. And remember, this is the options bit in the data packet that we talked about, and the polarity is the exact opposite of what you expect. Your system is running along quite happily and is synced. We played out this DMX refresh on all the universes. It got synced. We keep sending out DMX refresh, but there's no sync. Nothing changes. These don't get acted upon because they're not getting their synchronization. But after 2.5 seconds, after the timeout, what happens then depends on the force sync bit. If force sync is 1, then it just goes freewheeling. It just starts freewheeling again and playing out these packets. But if force synchronization is 0, these packets here in the light yellow don't get acted on. The look that you got all the way back here on the very left-hand side of the slide will stay there forever. No matter how many data packets you get, it's been told to force synchronization, and so it's just going to sit there for a very long time. Michael, I see you're jotting down a question. Is there? Okay, great. So before we get into transmit timing, I think I'll poll for questions again. Are there questions around the room? Or just hit the raise hand button underneath the attendee list if you want to ask a question.
I have a question.
Yeah.
You mentioned a few slides back that there's no consideration protocol.
And Jeremy, we see that you've raised your hand. We'll unmute you after we've finished the question in the room.
There's no consideration for genlock in this protocol. So if you wanted to synchronize your media server with your console, there's just not an option for that.
So the question was, if this doesn't do genlock, if you need to synchronize your media server with your console, how do you do that? A suitably clever implementation could pick one to serve as the master and then have the other one listen to it. So for example, if you wanted to lock everything to your media server, it's going to be asynchronous. It's going to be coming about every 40 milliseconds. Your console could listen to the media server, run a software PLL, a phase lock loop, and sort of know that, okay, I need to get this data out now, and then kind of lock to it. In a reasonable network, you can do that to within a few milliseconds.
And the case here is important to know is a lot of the media servers, contain Genlock these days. So you're typically needing to sync, the entire show with the cameras, with the truck, the video truck, and everything else. So you've got the Genlock coming into the media server, and then it could basically, you could route, or any other device, you could build an appliance to do this as well. Okay. That would then serve as the Genlock source.
Could you theoretically send a single universe of sACN from the media server to your console?
So the question.
Console sync on the universe?
Sure. So he was asking, could you have your console send a single universe of sACN to your media server, or the media server send it to the console, and then sync to that? Absolutely. Yes, you can.
That'd be probably easy.
So Jeremy has a question online. Jeremy, I'm going to unmute you. You want to tell us what your question is? All right. Jeremy, are you double muted? We're not getting your... Yeah.
I have Jeremy's question.
Yeah.
He was thinking that you mentioned the value in this forced sync bit as a counterintuitive choice. Can you also give us some insight into how that evolves, so maybe we'll have key to unlocking this way set?
If I have priority 1, 2, and 3, is my top priority 3 or my top priority 1? Are you 0? Are you and or nan? I would have to go back through the drafts to understand. Do you remember, Scott?
I don't remember the specifics. The way a lot of these things evolve in the standards is that the names change over time, the functionality changes over time, and so yeah, sometimes you end up with where you land is you forget to rename something, or the logic may be intuitive to the people in the room at the point where you're talking about it, but later you go back and look at it, it might seem less intuitive. The bottom line here is the functionality is well defined. It's just the state of the bit might be counterintuitive to what you were thinking it would be if you didn't read the text.
Any other questions coming in?
Yeah, I got one.
Yeah.
So a slide back, I believe it was, you showed 3 universes. And you said the latest packet takes priority. So if you say that middle one, let's say that for the second packet was not sent, it would just take that first one.
Correct. If this packet gets lost,
correct.
So if that packet gets lost, then yes, it's going to be, because that's the most recent it's going to see, and that does happen. So the standard joke is, spherical cows, frictionless surfaces, and error-free communication networks. We've long accepted in DMX that data can get lost, but there's another packet coming along 25, 40 milliseconds later. The same thing applies here. There can be visual artifacts. Just try and minimize it, use good networks, use good cables, and hopefully that minimizes the problem. But yeah, so his question was, if this packet that I'm pointing to now gets lost, what happens when the sync comes? And at that point, the receiver never saw this packet. This would be its most recent. And that can lead to visual artifacts.
But in a well-behaved network, you should be seeing, very little, if any packet loss.
I mean, just to give you an idea, in a well-behaved network, the bit error rate requirements, typically, we have to do days and days of traffic at 10 gigabits and see no packet loss. All right. Well, I think we will continue on then. I want to talk about a little bit for recommendations for transmit timing. The standard says that you may want to wait a few milliseconds after sending the last data packet before you send the sync packet. This allows time for both for everything to propagate through the network, but it allows time for the receiver to be ready to present that data. Sometimes a receiver has to do, depending on how it's implemented, if it's FPGA or software, sometimes it has to do formatting, color space conversion, scaling, all of this.
Calibration data.
Yeah, all of this, gamma correction. All of this can take time. And so by waiting a few milliseconds after you send the data, you allow it time to do that. And that's really what we show down here. You know, we send a DMX refresh, you know, all the stuff in this sort of light gray here. You send three universes worth of, a refresh for 3 universes worth of data. You wait a few milliseconds, and then you send the sync packet.
And this is probably one of the most understated things I would say in the standard is, you know, the fastest way to have poor sync performance is to try to send that sync packet as fast as you can after you send the last universe of data. I can guarantee you, if you put it, you know, with no daylight in between, you're likely to have issues with that last universe syncing properly. So giving a little bit of daylight in between here really does make all the difference in the world. And allowing, as Eric said, the data to get through the network and also the fixture to, you know, take a breath and process the data and have it ready to output. And this is kind of another key thing. It's a little more on the receiver side, but while we're here, is if you're receiving, if you're in a synchronized system and you support sync, you'll want to do all of the processing of the data that you can in advance before you get the sync packet, so that all of the gamma correction, calibration, you know, applying calibration values to the map, anything else that you have to do, which in a moving light can be a lot, in an LED fixture can be a lot, that you've got all of that data in the buffer ready to latch it to the LEDs as soon as you get the sync packet. The more you can minimize that kind of delta of things going on, the tighter the synchronization will be of what the user sees.
And when you're in an IMAG type application, obviously you don't want to add delay. Remember the 30 millisecond guidance that we gave earlier for synchronization? So generally, you know, if you're eating up a few milliseconds for this, you're still well within your human visual perception. Now, this delay is especially important if you're doing the administrative prioritization of traffic that I discussed earlier. Because if you set your sync packet to get absolute priority and your data packets are best effort, the network can reorder these packets. If you send them back to back, your sync packet can propagate through the network faster and arrive before the data packet it was supposed to sync. So, how many milliseconds? Well, how big is your network? What's the worst case propagation time? What other traffic do you have going on? I believe the recommendation at the standard, and I don't have the text in front of me, is effectively a user configurable value. A couple of milliseconds, it's going to be really testing for your market. We can't give you a number. 100 milliseconds is too high. 500 microseconds is too short. Find something that works for you, and maybe make it tunable way down in the advanced, double advanced. I really mean it this time, advanced. With time, we may settle on a best practices. I don't think we have that yet.
No, it's too early. It's too early at this point to give a solid recommendation of use this number and you'll be fine in 95% of the cases.
The next recommendation, and this is Eric's recommendation, this is not a consensus recommendation, is that you group packets into bursts when sending a lot of packets. If you're sending 100 universes of data, and you send them all out at once, they all hit your network. If you have anything that isn't able to swallow that at full rate, you can use packets because you'll overflow buffers, you'll overflow queues. So my recommendation is that so you know, if I'm sending, and I show it here in the green, you know, in this case, like you send a burst of 2 packets, you wait a brief period, and then you send the 3rd packet. My recommendation is that you make each burst of data smaller than the receiving OS's UDP buffer size. What size is that? I think Windows used to default to 8K for a UDP buffer. You can tune that. I haven't kept up. What OS is your receiver? You don't know. So the point here is just that don't dump 100 universes on the network simultaneously out of your media server at 10 gig. Burst it out a little bit. It just makes the queuing behave better. And again, most systems won't need this, but if you've got your 100, 200, 300 universe media server, it's something to keep in mind. You know, these delays are microseconds. Most OSs, when you introduce a delay, a 1 microsecond delay means whatever the scheduler quanta is. and just kind of do a survey of the market to find out, what receivers your customers are using, how big are the buffers, and where do they start to be getting too fast. It is not uncommon to have a 10 gig media server going to a 1 gig switch out in the rig, going to a 100 meg or even a 10 meg device out in the net, going node out in the network. So this is just about not overflowing that when you can. Scott, do you want to talk about receiver startup?
Sure. So as we talked a lot about the transmitter side, so we'll talk a little bit about the receiver side here. There's a little bit of ambiguity depending on how you read the standard in the startup behavior with the forced synchronization bit. So when you first start getting packets, you don't necessarily know if they're going to be synchronized or not. So when you first get a packet, an example would be is if I'm in a running situation here and I've got everything synced, and then I reboot as a fixture, I get rebooted. When I first come up, when I get that first packet of data, I may not know if sync is actually functioning, if it's active or not, until I see the sync packet. So a good practice would be that you might consider is when you first come up and you support sync and you see that there is a sync address in the data packet, that you might wait until the next data packet comes along or the third data packet comes along and you haven't seen a sync packet before you just start freewheeling. If you see a sync packet, then obviously you know that you are in the synchronized state and you follow those rules.
Generally, it might just be a good idea to honor the forced synchronization bit in this. It's not defined that way in the standard, but if the bit is cleared to say, force synchronize, just wait however you need the long to until you get the sync. And if it's set to allow freewheeling, then freewheel. But
I think we do actually have, I think in the standard it does, and this is kind of where some of the interpretation differs. Typically, and my reading on this is a little bit different than Eric's reading, so that's why you'll hear a little bit of maybe disagreement in us on it here. As I view it, and my recollection of it is that when you first start up, you typically start out in an unsynchronized state. So if you're in a system and you've got a sync address set, but you've never seen and you have the force sync bit set for that matter too, but you have never seen a sync packet yet, then you are able to freewheel. So until I get the first sync packet, I'm not in a synchronized state. It's only after I've gotten that first sync packet that now I'm in a synchronized state. Now you have to obey the rules of the forced sync bit.
And so we actually put the text from the standard here, and this is slightly abridged, but you can read this and decide for yourself. And honestly, this is not a mandatory standard. Do what makes sense for your customers in your market. The standard doesn't say, perhaps that was an oversight, but, and Matthias, this should really answer your question. Our belief is that any standard written, any device, receiver written to the 2009 standard that followed the standard should have absolutely no trouble receiving synchronized streams. The actual 2009 text for the bits 109 and the bytes 109 and 110 that carry the sync address, and the receiver options bit 5 said, basically receivers shall ignore. In standard Z's, that means you are obligated to do that. As we all know, software is bug-free and completely follows every standard to the letter, so I'm sure this is fully implemented. But if you find something that is not, you at least now have basis to go back and yell and demand your firmware update slightly sooner.
And the text for those fields, these were originally reserved fields, so they didn't have any prior use in the 2009 standard. They were placeholders for us to come up with something clever to do, which is what we did here. So, and the text again was very clear of that a receiver should ignore that field unless it knows what to do with it. So, again, 2009 built receivers should be perfectly happy in a mixed system with synchronization going on Obviously, the devices that support sync will be synced. The older device, non-sync aware devices will just free run.
And senders that were written to the older standard look identical to newer receivers, so there should be full interoperability. We are closing in on the end. We just have 4 or 5 slides left. We're going to get into some pretty pedantic stuff soon, and so I just wanted to take a moment to poll if there are questions. And again, you can submit them to Michael Lay via the chat panel. You can hit the raise hand button, or you can ask questions around the room. All right, and we'll do Q&A at the end also. So, all right. Another thing I need to emphasize, as many of you know, this existed in ArtNet and was rolled with some improvements into E1.31. If I have an unchanging universe of data, rather than chewing up network bandwidth, sending the same thing over and over and over, you just don't send it, because you don't need to keep sending changing data. The improvement in E1.31 was that we actually send, if I'm doing a fade, and then it stops, I actually send the last look 3 times, just in case packet loss. You know, statistically, most networks will lose very few packets. If you lose 1 packet, you'll get it the second time. If your network can't get 3 packets through, you've got serious issues. Statistically, this is just making sure that you get the last look. If your last look was a bump to all, you don't want the stage sitting in dark, you know, or sitting white. But what that means, we're showing the end of a fade here. So we have a crossfade. Here's the end look of the crossfade. That end look is repeated and synchronized 3 times, but then it's suppressed. Nothing is changing. I don't send it. But the sync packets continue. Why? They might be synchronizing other universes. You know, if one node, if one native device is receiving universes 1 and 2, and another one is receiving 3 and 4, the one that's, if 1 and 2 aren't changing, 1 and 2, the node that's getting 1 and 2 is going to see no data packets. But 3 and 4 are changing, and the sync packets go to both nodes. So as we show here, these sort of ghosted out data packets are not sent because they're unchanging data, but the sync packet is still coming. I point this out to developers. Don't crash, please. That's why I point this out. It's kind of something you don't think about, but it very much can happen. And then when a fade or a move or a bump starts to happen again, you get data packets in sync. This can happen and will happen all of the time. And we will make this recording available publicly, and along with posting these slides. So you can hand these to your software developers. You can refer to these. You can send us corrections, please. These were thrown together somewhat quickly. I threw this in for an example of how to, early on we talked about prioritizing universe 27 if it's a sync-only universe. I threw this in an example of how to do this, mostly so you would have it for reference if you need it. Most networks will never need this. We get in, and most of the time, you know, a gigabit, the longest packet in a gigabit network is 12 microseconds. How many 12 microsecond delays do you have to have before a human can see it? The answer is a lot. But if you have slower networks, if you start having lots and lots of other traffic, if your media server operator is sending tons of high definition video to their media servers and it's overwhelming, so you're getting congestion delays on your backbone links, and you need to prioritize your traffic, this is how you can do it. Hopefully you'll never need this. Most systems won't, but I wanted you to have a reference of a starting point of how to do this.
And typically, you know, one key point here to remember is the point where QoS starts to make a big difference is if you're in an oversubscribed network. So as long as you have plenty of bandwidth available, QoS really isn't going to make much difference for you. It's only once the point where you've got so much congestion going on that you need to start worrying about it. And my philosophy is on an entertainment network that is show critical, if I've got that much congestion where I'm having to start worrying about QoS, I need to upgrade my network.
Or separate out your network.
Or separate it out, partition it. You know, there's a lot of easier ways, in my opinion, to solve the problem before you start going down the QoS rabbit hole.
Yeah, and if you are building a theme park, if you're building a permanent multi-venue installation, then you need qualified people. I mean, we've proven that these protocols can work in gigantic networks. But at that point, you're going to have the qualified people who can really do the multicast management and configuration for you.
Yep.
All right, we are mercifully at the last slide, and we are not too far over time. Just a few provisos, quid pro quos. These are some things we thought you should know about. Scott, you want to talk about multiple active sync sources?
Sure. So the standard does allow you to have multiple sources on a network, because you do. On a big show, it's not uncommon to have one console driving conventionals, one console driving moving lights, and another console driving media servers, all sharing the same data network. And we have carefully architected everything so that it does allow you to have each of those can be running on their own universes with their own sync groups, and everything is perfectly happy. So you can have multiple sources, each providing sync to the universes they're controlling. The standard really does not allow for, you could be clever and try to do it, but as we kind of talked about in the Genlock case earlier, it's typically not intended that you would have one console A providing sync for universes that originated by console B. You really kind of want them all coming from the same source for a given set of sync groups.
The other thing that where you can get into trouble is if I have two consoles sending universe 1 synchronized to, and each console is sending sync, what's happening? The node is now getting two sync that are fighting with each other. Don't do that. My personal recommendation, and this is based on nothing in the standard, it is common in these kind of networks to have an architectural control system at a lower priority and a entertainment control system at a higher priority, so that if you shut down the console, the architectural takes over. If you are seeing multiple data streams that are synchronized, have the sync honor the priority that's in the data packets. If you're taking the data from the console, then use the console sync packet. When you shut down and you fall back to the architectural system, honor the priority. Take the sync from the architectural at that point. Again, my personal recommendation only, not in the standard.
And the same thing goes for merging. When it comes to merging, I really wouldn't recommend trying merging with sync. I think your results are going to be a bit unpredictable. If you've got two universes that are coming from different sources that are set to the same priority, and you're doing an HTTP merge, sync is really going to kind of start to become meaningless, in my opinion.
And the other thing is, yes, Michael, sir.
I have a question for John. If multiple consoles can send out different universes, why can't we use a single sync packet for all universes?
So the reason, and we talked about that.
So in case you can't hear the question, because this is a direct
Oh, sorry.
if multiple consoles can send out multiple universes, why can't they all use one sync?
And we talked about this a great deal during the writing of the standard. And could you configure it that way? Sure. If your console allows you to do the configuration, you could configure that. However, the behavior could be a bit undefined because you don't necessarily, so for a given, let's talk in terms of video for a minute. So I've got a frame, which is a given look. And I've got this frame of data coming out, this frame of video coming out from my console. And then I've got another device that is trying to send the sync source, send the sync packet. I don't necessarily, as that other device, I don't necessarily know which frame everybody is on. So it would be very easy for me to send the sync in the middle of, universes 1 through 5 have sent out frame 1, universes 6 through 10 are, sending out frame 2 right now, and I send my sync in the middle. I don't necessarily know where it's at. So it's very easy to create pairing in an image if you were to do that.
And this protocol is really intended to provide, milliseconds and multiple milliseconds of sync. If you really need the Genlock, if you're trying to sync together multiple media servers, or you're trying to sync together a console and media server, there are network protocols that can do this with microsecond and nanosecond resolution. If you're really trying to Genlock together over a network, 2, 3, 4 media servers, you really need to be using some of the better PTP profiles, Precision Time Protocol, IEEE 1588. Those are really about nanosecond level sync. And then you can use that to sort of gen-lock your frames together. And there are some SMPTE standards, at least in progress, that talk about basically doing gen-lock over PTP. But that's really doing pixel sync, single-digit microseconds, tens or hundreds of nanosecond level sync. And then this is really about those media servers playing out. If you're trying to all sync to one, software PLLs without that trying to sync together, you just get into the tearing that Scott talked about. The other outcome of this is because that the sync and the data are supposed to come from the same source, make sure that your receiver, if you're doing notes where the data packet is coming from and notes where the sync packet is coming from. And if they don't match, treat it like the sync isn't there. Whether you should use the source IP address or the SID is a matter of some debate on which I have no opinion. Now, Scott looks at me shocked.
Yeah, I am shocked that Eric has no opinion on this. I'm kind of in the same respect. Personally, I normally look at the IP address on some of my stuff, but it's really kind of up to the user. I don't think we specified this in the standard. The next point here is also important, is that it is possible that the sync address could change from packet to packet. So at some point along the way, especially if your system is in the process of being configured or somebody's troubleshooting it might change in the console what sync address is being used. Now, as a fixture, when I first came up, I came up and I saw that sync was going on, and the sync address was universe 1. So I subscribed, my data packet might be on universe 2, but I also subscribed to the multicast group for universe 1 so that I would get the sync packets. Well, now the user goes along and changes it to the universe 10 for the sync group. I need to be monitoring that data packet to know when that sync address changes that I need to unsubscribe from the old universe and then subscribe to whatever the new universe is in the multicast group to get those sync packets. They won't necessarily just come to you. You have to, do the multicast subscription properly.
So in E1.31, you are able to, it's primarily built around multicast, but you are able to unicast. If you have tons of universes going point to point, or you want to do some more configuration, you can unicast. The standard doesn't explicitly say this, but it makes no sense with that. Sync packets always have to be multicast. It makes no sense to unicast a sync packet.
There was some disagreement in some corner case edges where somebody might want to do this for some reason, but generally speaking, it's a horrible idea to unicast the sync packets, because the whole point of sync is that everybody gets the trigger to perform synchronization at the same time, and if you're quietly whispering into each device's ear, sync now, separately, then you've just kind of like blown the whole point of sync.
So, this isn't really sync related, but avoid Wi-Fi with this protocol. Wi-Fi is terrible at handling multicast data. The technical reason being that, the newer Wi-Fi standards, 600 megabits a second, Y gigabit, all these really fast data rates. But your Wi-Fi access point has to handle multicast at the slowest supported rate. The slowest supported rate in 802.11b is 1.5 megabits. You are taking your 600 megabit access point and running it at 1.5 megabits. Also, multicast traffic is bundled into the beacon. It's called the DTIM interval. So which goes out every 100 milliseconds, which means your sync packets will be delayed by 100 milliseconds. As Max Wertheimer told us, you're going to get some pretty weird visual artifacts. If you have to use Wi-Fi, and people think of Wi-Fi as cutting the Ethernet cable and putting a wireless in between, don't think of it that way. But if you have to, use a Wi-Fi system that supports multicast to unicast conversion.
And even unicasting, even if you're unicasting because you're using Wi-Fi, it's important to remember Wi-Fi can, correct me if I'm wrong here, but Wi-Fi also tends to be fairly bursty with the traffic. It doesn't transmit them at the same rate as you're seeing them across the wire. It tends to kind of burst things.
Wi-Fi is terrible at handling this kind of data. If you must use it, I mean, sometimes you have to do it. Sometimes you can't run the wire. But avoid it. The other thing I want to point out is that when you're debugging sync tools, it's really tempting to put your phone at the video screen and take a video and say, oh, look, everything isn't synced. Due to the effects of inter-frame video compression, you can be perfectly synced, but because of the way compression works and the macro blocking within MPEG, your video can make it seem like you're not, even the high frame rate stuff. So it's a good tool that can help you debug sync, but single framing through your phone's video isn't necessarily going to give you what you want. A good camera that supports MJPEG or something that only uses inter-frame, in other words, that compresses within the frame but not across the frames, is what you really need to debug this. And honestly, if you're reaching that point that the Mark 1 human eyeball can't see it, maybe it doesn't matter.
It normally matters more of a case for when you're doing broadcast stuff, I would say. And then you normally have all kinds of other tools for looking at it as well. All this being said, I will admit, I use my my iPhone all the time for doing this. So I will do a slow motion video, and then I will single step through. And I know that depending on the case, it may be lying to me a little bit, but in terms of the best tool in my pocket to look at things, it's still there, but just know it's not necessarily 100% accurate.
All right. So we're at the end of the presentation. We're going to get to Q&A shortly, but I do want to drop this in everybody's ear. Support for developers using RDM protocols. I truly believe this, using ESTA protocols. I truly believe this is the best resource on the internet. This is technical discussion of ESTA protocols. It is a very good signal-to-noise ratio, and there are many members of the task group and highly qualified people who read this. It is common, nothing guaranteed, to get a high-quality technical answer in a day or less. We've had some very detailed discussions, and there's an excellent archive of old material. Anybody on the internet, guests, can read and search. We're not locking you out. Look, if you're trying to understand something, read it and search. And if you can't find what you want, register and post. The thing you need to know is that your first post won't show up until it is approved by the moderator, which is Scott in this case. It just keeps the, You
want to buy a Rolex watch? How about some sunglasses?
It keeps the forum spam down. But once we've, so make sure that your first post is technically substantive. We realize that you're actually interested and not just a duplicate of a previous post. We've all read the posts. The spammers now just try to duplicate older posts. But
yeah.
I mean, if you put something technically substantive in there so that it's clear that you're a person who's really interested in this, and then your account will be instant posting from then on out.
Yeah, and you don't have to be a developer, a highly technical person. Any real question is very distinguishable from a spam post, no matter how sophisticated they try to get. It's immediately obvious. So yeah, as soon as you create an account, once you do your first post, you basically the first post is moderated. Then after that, you're set up as a full user so that you can then post freely and nothing is moderated. It's just that way it keeps the spam out. Most of the task group members are subscribed to all the forums, so whenever a new post is made, they get a notification. So keeping the spam out keeps the spam out of all of our inboxes. But I've also set up a Streaming ACN dedicated forum on there as well just the other day. So yeah, if you have any questions on sync as people are implementing sync or trying to use sync or have questions about it, or anything else about Streaming ACN, you can ask it in there as well. I mean, if it's, how do I use this product, we'll probably punch you off to the manufacturer, but for technical questions about the protocols. So, Q&A. First, I would like to ask, just for some feedback in general, was this helpful? Was this what you were hoping it would be? And just please use the check mark or the X, just to kind of let us know what you were thinking. And with that, I think we have some questions. Did I see you, Michael? Did you collect some questions for us?
No, I would just comment that if anyone wants CT renewal credits for this session, they should just reject.
Okay. Any questions around the room? All right. Well, we got 3 yeses, a couple no responses, and and no no's. But okay, do we just unmute everybody? Okay, so all the lines are unmuted if you did want to ask a question verbally.
No questions? Is everybody awake? Did we put you to sleep?
Uh-oh, we're getting some no's here, so.
Actually, I think those have just been there.
Oh,
The exclamation points, they've been there for the whole time.
oh, no, okay. Yeah, you had a question.
Can you speak to recommended infrastructure and what kind of?
So, given that I work for a networking company and I'm not here to sell anything, I'd rather not get into specific vendors' products.
Sure.
I would be perfectly happy to have that conversation in another context.
I think generally speaking, you want something that's going to support IGMP, that's going to support that. One of the specific things of
well, yeah, I mean, you know, IGMP snooping, but even in that case, you know, the general saying is the more money you spend on a switch, the more money you have to spend on configuring it. So don't go buy the best thing you can and expect it to just work.
What about unmanaged?
Most unmanaged are pretty good. Web managed, we actually had a seminar, a roundtable earlier about IGMP, PIM, and multicast management. If you don't have an IGMP querier in your network, your multicast snooping isn't doing anything. So most networks that have not been actively configured are treating all of your multicast like broadcast anyway.
And so that's the thing, that's really the key thing to be aware about is you want to look for those features because otherwise, an unmanaged switch, it'll just be turning it into broadcast traffic. And if you're on a small network, that's fine. But as you start scaling up, there will be a point where you'll fall off of performance if it's turning everything to broadcast for the whole network versus actually using multicast.
Yeah, don't buy the cheapest thing because they have problems with multicast. But buy, you know, middle of the road, and if you buy something really good, it's because you're doing a very large network and you have the people and the skills to configure it. So, all right, last chance to throw in questions. All right. Well, thank you, Michael. Would you be so kind as to hit the stop recording button on the lower corner? Thank you very much, everybody, for joining us. Hopefully this was interesting. Please, you know, keep an eye. We are intending to do more of these roundtables in the future on various topics. You know, a lot of what ESTA does is educating and, you know, getting word out there. And, you know, we're all about improving interoperability. So thank you very much.
Cool. Thanks, everybody.